So the first one you dealt with is when you were looking for the Laplace transform of a constant 1. And you said the Laplace transform of a constant 1 is simply 0 factorial over s0 plus 1. Because a constant 1 is the same as t raised to power 0. When t is raised to power 0, it is 0 factorial over 0 plus, isn't it? Then after that, you said the Laplace transform of t, that is t raised to power 1. So it is now 1 factorial over s into 1 plus 1, isn't it? Giving you 1 factorial over s squared, isn't it? Which is just that. You went ahead and you found that the Laplace transform of t squared is just 2 factorial over s2 plus 1, isn't it? So that is giving you 2 over s cubed. Then generally, you found out that the Laplace transform of t raised to power n is given by n factorial over sn plus 1, isn't it? So in case you want to find the Laplace transform of a function like t raised to negative 5, if you want the Laplace transform over t raised to negative 5, because the factorial notation is working with a natural number, then you have to do it by definition, isn't it? So if you do it by definition, then you know the Laplace transform of this will be, you integrate from 0 to infinity, then our function f of t is t raised to negative 5, then exponential negative std dt. So you do it by parts until you are able to find the final transform of that given function, isn't it? Then you also went ahead and you found out that the Laplace transform of exponential at is given by 1 over s minus a. You went ahead again and you found out that the Laplace transform of cos at, you found cos at was using the quotient rule, so that was becoming s over s squared plus s squared, meaning for the cosine numerator was differentiable, for the sine the numerator was a constant. So it means when you were looking for the Laplace transform of sine at, then the numerator was a constant. So it was now a over s squared plus a squared. For the cosine was using the quotient rule, isn't it? But for the sine, the numerator was a constant. You see, you can change this into, you can actually change this. You can change in form of a chain rule when you have a product of two functions. When you now know that if this one is cos at, so if it is going to be cos at, then the sign here is negative, isn't it? So it means you found out that the Laplace transform of cos at is given by s over s squared minus a squared, isn't it? And you went ahead, you found that the Laplace transform of sinh at is given by a over s squared minus, because in at this for the sinh it was negative, was coming in the middle, isn't it? Then after that you went ahead and you found out that the Laplace transform of t raised to power n f of t, a product of a polynomial function t raised to power n and f of t, where f of t can be any function, isn't it? It can be an exponential, it can be a trigonometric, it can be hyperbolic, it can be any function. That was given by negative 1 raised to power n dn over dsn of the Laplace transform of f of t, isn't it? Of the Laplace transform of s of t. So that is how to get, if you have a product of t and a function f of t, isn't it? The f of t can be exponentials, anything. It can be cosine function, it can be sine, it can be cos, it can be anything, isn't it? Then you went ahead and you found out that the Laplace transform of the first derivative, the Laplace transform of the first derivative you found was given by S, the Laplace transform of y minus the y of 0, isn't it? When x is 0, isn't it? Then you went ahead and you found out that the Laplace transform of the second derivative is given by s squared, the Laplace transform of y minus s y of 0 minus y prime of 0, isn't it? That was the Laplace transform of the second derivative. Now, we now want to see how the task here is to know how to actually get these general definitions of Laplace transform by definition of the Laplace, isn't it? Once you are able to do that, you know there's only one thing which is involved for you to be able to find all the Laplace transforms, isn't it? So for you to get all the Laplace transforms, it means you must know integration by parts, because it will be a product of functions, isn't it? You must just know it is only integration by parts. So we now want to see maybe how 2 or 3 of these functions are coming about. Then the big issue is how do we now use it to solve ordinary differential equations. Are we together? How do we use it to solve ordinary differential equations? So when we are going to use it to solve ordinary differential equations, or when you are going to look for the Laplace transforms of different functions, will be direct as per the definition, isn't it? So what will now come in is now when we are now looking for the Laplace inverse, meaning if you take Laplace the other side, it becomes Laplace inverse of that gives you back your function, isn't it? So post Laplace inverse, what do you need to get a Laplace inverse of a function, isn't it? Meaning one thing you need to know is you have to know the Laplace transform of standard functions for you to be able to get the Laplace inverse of any function, isn't it? The second thing you need to know is how do we complete a square of quadratic equations, isn't it? That is the most important part. When you want to get the Laplace inverse of different functions, you must know the method of the completing square. Are you seeing that? So the method of the completing square is the most important when you'll be dealing with the Laplace inverse functions. Are you seeing that? Then after that, the most important of all is resolving into partial fractions. So there are 2 things you have to master for you to do anything in Laplace transform. When you are going to deal with the Laplace inverse. So when we are going to deal with the Laplace inverse, it means we are going to go back to the original functions, isn't it? So for you to deal with the Laplace inverse functions, the Laplace inverse, there are only 3 things you need to know. The first thing you need to know is the Laplace transforms. You need to know the Laplace transforms of the standard functions, isn't it? You have to know the Laplace transform of standard functions. Then the second thing you need to know is the method of completing square. The method of completing square. You have to understand the method of completing square from quadratic equation. So the method of completing square, somebody will give you found the Laplace transform of a given function to be maybe 3s over maybe 2s squared, isn't it? 2s squared maybe minus 4s plus 2. So if you look at this case, before you can see the numerator, we have a quadratic equation, isn't it? So the first thing you have to do, are you able to factorize this quadratic equation into factors, isn't it? If you are able to factorize it into factors, then it means you can resolve it into partial fractions. Are you seeing that? And if you are not able to factorize it, then it means you have to use the method of the completing square. So the first thing, in fact, there's that part of the Laplace transform I left out. So before I go to that, we did not talk about the Laplace transform when you have a product of the exponential function and another function, isn't it? Like when you have the Laplace transform of exponential at maybe equals wt, isn't it? You know the cos was using the quotient rule, meaning there was s in the numerator, isn't it? So you know cos was s. It was, if you were looking for, the moment you were looking for the Laplace, the moment you are looking for the Laplace transform of cos at, you got s over s squared plus a squared. But now we have cos wt, meaning instead of a, where they say we put w, isn't it? So for the cos, because we have the exponential at, and the Laplace transform is going to be exponential at, you product it with a, so it will be same base, you add the powers, lots of indices, isn't it? So it is like you are going to have negative st plus at. So if you factorize a outside, you will have s minus negative in bracket s minus a, isn't it? Are you seeing that? So it means our s is no longer s, it is now s minus, where there is s, you now put s minus a, isn't it? We use lots of indices. The same if you have for sine, if you have for exponential at, sine wt, you know very well sine was given by a over a squared plus a squared, isn't it? So you know when it is sine wt, meaning where they say you put w, isn't it? Where they say you put w, because exponential at is going to multiply by exponential negative st. So if you factorize negative outside, you are going to get s minus a, isn't it? So it means where there is s, we put s minus a, isn't it? So that was the Laplace transform when it is a product of an exponential function and another function, isn't it? Like trigonometrical hyperbolic. So when it is hyperbolic, you simply change the sign here, meaning if it is cos, it means this is minus, isn't it? Yeah. If it is sinh, then you know this is minus, isn't it? So those are some of the things you need to understand. You have to design a set of some sort of methodology of mastering the Laplace transforms of different functions, isn't it? That is where we are starting from. The Laplace transforms of different functions. Once you know that, then you will be able to get the Laplace inverse of any function. You will be able to solve any ordinary differential equation. Are we together there? So if you look at this denominator, which number gives you a product of 4 and a sum of negative 4? Negative 2 and negative 2, meaning this problem can be factorized, isn't it? Negative 2 and negative 2. So if you factorize that, you will get, oh, in fact, this was just if you factorize 2 outside, 2 was common. So let us just finish with this part. So this is 3s over 2 into s squared minus 2s plus 1, isn't it? So after that, you can now see you have 3 over 2 outside there, isn't it? This is 3 over 2. Then inside you have s over s squared minus 2s plus 1. You found it is s minus 1 squared, isn't it? It is s minus 1 squared. So if you look at this, there's no Laplace transform of this kind. We need to resolve this into partial fractions, isn't it? Because when it is s minus 1 squared, you must have it plus something or minus something, isn't it? It's when you can have this as exponential this and this. You know, if you had it maybe plus 3. So you see, when you add it maybe plus 3, meaning they are 2. Why? Because s minus 1 will be like s minus a, isn't it? So in the numerator, you must also have s minus a, then you add plus 1, isn't it? So that you separate, the first part will be this over this, the second part will be this over this. So this over this will become exponential something cos, isn't it? Then plus the other part will become exponential something same. Are you seeing that? Are we together? You talked about all that, isn't it? So, our main concern here, we will see how to use the method of completing square where it applies, and we will see how to use the resolving into partial fractions where it applies. Meaning what will be guiding you is the Laplace transform of those standard functions, isn't it? You will be able to know, do I need to complete the square or do I need to resolve into partial fractions, isn't it? You see that? So you will either use the method of computing square or you will resolve into partial fractions. So you have to know how to resolve into partial fraction. If you have linear factors, you have to know how to resolve into partial fraction. If you have quadratic factor, you have to know how to resolve into partial fraction. If you have repeated linear factors, you have to know how to resolve into partial fraction. If you have repeated quadratic factors. Are we together? So let us maybe see one or two functions, how to get Laplace transform of one or two functions. Then we now use that to deal with it. Meaning Laplace transforms are things you must know because you will be using them. Are you seeing that? It is what we want to use in the ordinary differential equation. So it is what I expect you to know. It is what I expect you, something you should know. So, for instance, when I want to get the Laplace transform of the first derivative, dy over dt. So what is the Laplace transform of the first derivative? Dy over dt, meaning our f of t, where there is f of t, you put the first derivative, isn't it? So we'll have, we are integrating from 0 to infinity, f of t is dy over dt exponential negative st dt. Now if you look at this, you know, for you to solve this with integration by parts, then it means dy over dt, for you to get it back to y, it must be integrated, isn't it? For it to be integrated, it means dy over dt must be dv. Are you seeing that? It must be dv. So you have to rearrange this so that you have, you are integrating from 0 to infinity exponential minus st dy over dt dt, isn't it? We have our dy over dt here times dt dy over dt, isn't it? So dy over dt must be integrated for you to get y, isn't it? So it means if this is integration by parts, our exponential negative st will be u, and the whole of the other part becomes dv, isn't it? And you know very well that when you integrate u dv, you're supposed to get uv minus the integral of vd du, isn't it? So the task here is to find uv and du, isn't it? So if you start from there, you have your u, you have here as exponential minus st, isn't it? So what is du? If you differentiate u with respect to t, du over dt is what? If you differentiate an exponential function, it remains the way it is, isn't it? Then you differentiate the inner function. If you differentiate minus st, minus s is a constant, you are differentiating with respect to t, meaning t is the variable, isn't it? So minus s is a constant. If you differentiate t, which is the variable, you get 1, isn't it? So minus s times 1, you get what constant? Negative s. So you differentiated both inner function and outer function, and you express them as a product, isn't it? The outer function is differentiating an exponential function. It remains the way it is, isn't it? Then the inner function is minus st. If you differentiate minus st, you get negative s. Because negative s is a constant, t is what you are differentiating with, the variable. Are you seeing that? If you differentiate t, you get 1. So it means in the end, you get your negative s. Is that okay? So that one, you now multiply both sides by dt, then you get du is equals to minus s exponential negative st dt, isn't it? Then there you have your dv to be, you have your dv to be dy over dt dt, isn't it? So what does that imply? See, look at this. See, dt will go with dt. What will you remain with? dy, isn't it? So it means for you to get v from d, you must introduce integral on both sides of the equation, isn't it? So it means integral will go with d, you remain with v, integral will go with d, you remain with y. Are we together? So we now go and do our substitution in the equation. The first part here, you know we are integrating from 0 to infinity. So you introduce your integral 0 to infinity, isn't it? So the first part, you start substituting the integral from 0 to infinity of u. Then you go, what is your u? Exponential negative s to dv. What is your dv? The whole of that, meaning you just report back the whole problem, isn't it? So you know dy over dt exponential negative s t dt, which was the original problem, is equals to what? uv, isn't it? uv is u times v. It is y exponential negative s st. Are we together? Y exponential negative st. Now, if you have v to be equals to y, this is what it implies. When you have, for instance, if you have y is equals to 2x plus 3, this simply means that y is a function of x, isn't it? But we said a function can be denoted by any letter, isn't it? So y is a function of x can as well just be noted as y is a function of x. You just use the same to avoid using a lot of unknowns. Are you seeing that? So like here, y was a function of what? Y was a function of, because you were differentiating y with respect to t, meaning y was a function of t, meaning it was in terms of t. Are you seeing that? Are we together? So it means when you are now substituting here, you have y, and this our y is a function of t, isn't it? Exponential negative st, then it is minus, you integrate from 0 to infinity. What is v? V is y, which is a function of du. What is du? Negative s. You take negative s outside. Negative times negative, it becomes positive s, isn't it? Then exponential minus st dt, isn't it? Then after this, you put your limits of integration. It was from 0 to, the limit of integration was from 0 to infinity. That one is still an integral, isn't it? Then you start substituting. It is supposed to be, in this first part, it is supposed to be upper limit minus lower limit. Then it is plus s. What is this? Y of t, or just, even if you just leave it as y here, or y of t, there's no problem. So even if you leave it as y exponential negative st dt. What is that? See, that is y exponential negative st dt. Meaning y is the function of t, isn't it? So where there is ft, you put y. You get it is Laplace transform of y, meaning the whole of this integral from 0 to infinity of y exponential negative st dt is this definition, meaning where there is ft, there is y, isn't it? So that is the Laplace transform of y, isn't it? Then in this first part, upper limit, you substitute infinity here. You know exponential infinity or negative infinity is 0. You simply go to calculate exponential, then you raise it to a very big number, isn't it? To start with, the big number stands for infinity, then the output will be 0, isn't it? So it means that is 0. Then if you substitute 0, you know, where there is that, you put 0, 0. So exponential 0 will be 1, isn't it? Anything raised by 0 is 1. So it means you remain with y of 0, isn't it? You remain with y of 0. So in the end, you rearrange 0 minus y of 0 plus s Laplace transform y. So you end up, you start with the positive part, isn't it? Which is s Laplace transform of, this is the positive part, isn't it? Then the negative part, 0 is 0, meaning you remain with the minus y of 0. Are you seeing that? Minus y of 0. Now you've now found this is the Laplace transform of the first derivative. Are you seeing that? Of the derivative of first order, isn't it? So this will be to be used, meaning you don't need to go when you want to solve a second order or first order, you want to solve an ordinary differential equation. You don't come and derive this. This is something you know, you've mastered. Are you seeing that? It is something you use, okay? It is not to be derived when you want to solve a problem. It is something you master. That is why it is good to know how it is coming about, isn't it? So that when we are going to use it, we are very conversant with this way about. So after this problem like y of 0, how does it come about? This y of 0. This is what it means, because you will be given the boundary conditions when you want to solve a differential equation, isn't it? You will be given boundary conditions. So if you are given the boundary conditions, somebody will tell you that maybe solve the given differential equation, maybe solve the second order ordinary differential equation, given that a dy squared plus b dy over dx plus cy is equals to maybe f a function of x. Are you seeing this? Maybe you want to solve a differential equation in this form, and you've been given when they will say when t is equals to 0, then they are telling you when t is equals to 0, y is equals to 0, and maybe dy over dt is equals to 4. Are you seeing that? Now, what this implies is this. Because you are differentiating, or this was x, so we are no longer talking about it, we are talking about x, isn't it? This was x. Are we together? You are differentiating y with respect to x, so you will be told when x is 0, y is 0, and dy over dx is equals to 4. So how are you going to transform this into Laplace format, isn't it? So what do you need to know? If you are differentiating y with respect to x, what you need to know is that y is a function of x, isn't it? So y is a function of x. So what you come here, how do you interpret this? Meaning you are saying when x is 0, y is 0. So it means where there is x, you put 0 to be equals to. So they're trying to say when x is 0, y is 0. So that is how this statement is denoted in Laplace. Are you seeing that? Meaning when, because y is a function of x. So they're saying when x is 0, y is equals to 0. So that is taking care of that open statement. Are you seeing that? Then again they will say dy over dx, you know that is the first derivative. So if y is a function of x, if you differentiate both sides, you get y prime is the derivative of that, isn't it? So they will write for you y prime of 0 is equals to 4. That is what they will write, isn't it? Meaning they are telling you that the first derivative is 4 when x is 0. Are you seeing that? So they are joining this and this in that form. Are you getting that? Because Laplace transform is giving you the y of 0 and y prime of 0. When in case you have the second derivatives, the second order derivative, ordinary derivative, isn't it? Are you seeing that? So when you see y prime of 0 to be equals to 4, it simply means when x is 0, y dy over dx is, the derivative is 4. Is that okay? Good. So, that one we've seen how that first order derivative could be transformed using Laplace transform, isn't it? Now, we've seen that the Laplace transform of dy over dt is given by as Laplace transform of y minus y of 0. Meaning y of 0 is a boundary condition, isn't it? It's a boundary condition. It is a value you will be given, then you just substitute there, isn't it? Then Laplace transform of y, for you to get Laplace transform of y, meaning you take Laplace the other side to become Laplace inverse, for you to remain with y, isn't it? And you know y is the solution of the differential equation, isn't it? So it means for you to get the solution, you must take Laplace the other side of the equation. And if this side it is Laplace, if you take it on the other side of the equation, it becomes Laplace inverse, isn't it? Like when somebody just gives you that sine x is equals to 3, meaning if you take sine the other side, you get x is sine inverse of 3, isn't it? If somebody gives you that ln of x is equals to 2, and if you take ln the other side, it becomes exponential. That is the guy. It becomes exponential. that is the inverse of ln. It's an exponential function. Very important. So when you are going to come, even when you are going to solve the differential equation with the d factor, you will come across a linear, maybe a linear first order differential equation. You will come across a part where you are looking for r, isn't it? And maybe you get r is the exponential of the integral of p dx, like that, isn't it? Then if you integrate p dx, maybe your p of x, you found your p of x maybe to be 1 over x. So when you substitute it there, then you end up getting r to be exponential integral of dx over x. Are you seeing that? So the moment you integrate this, you end up getting what? You end up getting exponential ln of x. So you should know the answer is x, because ln and and exponential function, one is inverse of the other. So in logarithm, you know that ln of exponential raised to power x, that's because you see the power of logarithm can be expressed as a coefficient. See there? Then you remain with ln of e is 1, so it's x. The inverse is the same because ln is the inverse of exponential. So it means exponential ln of x will also be x. And ln of exponential x will also be x according to laws of logarithm. So this is according to laws of logarithm, this is according to the inverse function. Are you seeing that? That understood? Yes. So, now, because we've seen how the first order, how we can transform the first order differential equation, what about the second order? The Laplace transform of d squared y over dt squared. Are we together? Now, how do we get the Laplace transform of d squared y over d squared? Meaning our function f of t, we substitute with this, isn't it? So the Laplace transform is from 0 to infinity f of t exponential minus st dt. So you can see our Laplace transform of a function f of t is equals to this, isn't it? So where there is a function f of t, we put the second derivative there, isn't it? So that is going to be, we integrate from 0 to infinity of exponential minus st d squared y over dt squared dt, isn't it? Are we together? Yes, we just rearrange. Maybe we've started with this, then that goes to, because the derivative need to be differentiated to come back up to y, isn't it? So for it to be differentiated, it must be dv, isn't it? It needed to be integrated, I mean, isn't it? It had to be integrated. Then what is to be integrated is dv. So you make it dv by rearranging, isn't it? So from there, you see your exponential negative st becomes u, then the remaining part becomes dv, isn't it? So you know very well that if you have integral of u dv, you are supposed to get uv minus integral of vd du. So in our limits of Laplace transform is from 0 to infinity. So we just substitute the values, isn't it? So from here, our u is exponential minus st. So if you differentiate u with respect to t, you differentiate exponential function, it remains the way it is. If you differentiate the inner function minus st is, if you differentiate t, you get 1 minus s is a constant, isn't it? So you just remain with that constant of the, to be the derivative of the inner function, isn't it? So that is du over dt, then you multiply both sides by dt, you remain with the du is equals to minus s exponential negative st dt, isn't it? Then you know your dv is what? The dv is the whole of that, isn't it? It is d squared over dt squared dt, isn't it? Are we together? So you know d squared y over dt squared can be written as what? It can be written as y double prime of t, isn't it? Meaning you have differentiated y twice with respect to t, isn't it? So for you to get v, you must introduce integral on both sides, isn't it? So from here, d goes with that, you remain with v to b. If you integrate y double prime, it becomes y single prime, isn't it? Are we together? Yes, if you integrate y double prime, it becomes y single prime in that order, okay? So you go on and you substitute the values in your integration by parts formula, isn't it? So we are integrating from 0 to infinity, and u dv is our problem, which is d squared y over dt squared exponential negative st dt to be equals to uv, isn't it? So u times v, u is exponential negative st, then v is y prime of t. So we'll have exponential negative st y prime of t, then you are integrating from 0 to infinity, isn't it? So we've substituted the values of that. Our v is y prime of t. I need this space. So after that, what do you get here? Then it is minus integral of vd, and what is v? Y prime of t. What is y prime of t? See, y prime of t is dy over dt. isn't it? Then what is du? Is negative s. So if you bring negative x outside, negative into negative becomes positive s, isn't it? Then you remain with exponential minus std dt. Then you start substituting, isn't it? So this first part, if you substitute the upper limit infinity here, exponential raised to infinity is 0, isn't it? Meaning the upper limit will be 0, isn't it? Then minus lower limit. Lower limit, when you substitute 0 here, when you put 0 in exponential function, exponential, anything raised to 0 is 1, isn't it? Meaning here becomes 1 and here becomes y prime of 0. What is t? You put 0, isn't it? Y prime of 0. Then in this second part, it is plus s. dy over dt is f of t. Are you see? So it is f of t exponential negative st dt. So it means that one is Laplace transform of what? That is the Laplace transform of dy over dt. Meaning dy over dt, if you put f of t, you find the definition of the Laplace transform. Are you seeing that? It is the Laplace transform of dy over dt. Is that okay? So where this Laplace transform of dy over dt, we are going to put its value, which we found in the first case. Are you seeing that? Isn't it? Because if you put f of t, yes, you will have f of t exponential negative st dt. So that is the Laplace transform of f of t. And our f of t is dy over dt, isn't it? So that one we've already found, isn't it? So we just substitute it, okay? So what do we have here? Here we now have 0 minus this, we just remain with negative y prime of 0, isn't it? Plus s, in bracket you put the Laplace transform of dy over dt, which we found was s Laplace transform of y minus y of 0. Are you seeing that? So after you've done that, you just simplify, isn't it? So if you simplify, you will get s times s. You start with the Laplace transform y, the positive part, isn't it? See, this s multiplies everything inside the bracket. So you'll end up getting the Laplace transform of, you'll end up getting this side I have the integral from 0, this is the Laplace transform of what? The Laplace transform of d squared y over dt squared. That is this part of the equation, isn't it? Because this is our function f of t. So it is the Laplace transform of f of t, and our f of t is d squared y over dt squared. To be equals to what? This is what we found. So you start with the positive part, isn't it? This s multiplies everything inside that bracket, isn't it? So s times s, you get s squared Laplace transform of y. Then s times that, you get negative s y of 0, isn't it? Then here we have negative y prime of 0. So you have to know the Laplace transform of the first derivative and the Laplace transform of the derivative of second degree, isn't it? So once you know the two, then it means we are now in a position to solve any ordinary differential equation using Laplace transform. So you see that we are now in a position to solve any ordinary differential equation using the Laplace transform. So when we'll be solving those ordinary differential equations, that is where we'll now be seeing those Laplace transforms by definition. What is the Laplace transform of exponentiality? You get 1 over s minus a. Then it means if you take the other side, you'll be getting the Laplace inverse, isn't it? Because at the end of the ordinary differential equation, everything will be Laplace transform. So if you get back the original solution, you must get the Laplace inverse, isn't it? Are we together? Good. So let us start with example number 1.